switch topics a little bit here. We are going to go into looking at phase changes and what is happening on the molecular level um, during phase change. And we'll go into vapor pressure and boiling point and all that. Okay. All right. So molecules, the molecular dance. So molecules in the liquid state are always in motion. Actually in the solid state too. I just can't move as much anymore. They vibrate. But molecules in the liquid not only vibrate, they also can rotate and also translate. Translate meaning they actually move, right? You guys know what rotate is. You can rotate in one spot, okay? But you have a lot more motion, right? Um, and we know that the average kinetic energy is proportional to the temperature. Um, so um, we we know that some molecules always have more kinetic energy than others, um, and others have less, right, than the average. So let's talk about the phase change of vaporization, going from a liquid to a gas. So how is that happening? Well, if you have water in a beaker, right, the water molecules at the bottom of the beaker is not the one that's going to evaporate first. Okay. So if you analyze it, this makes sense, right? Because the water molecules at the bottom, remember, have more hydrogen bonds, right? Because it's surrounded by more water. So it's not going to be able to escape into the gas phase. However, the liquid molecules, the water molecules at the surface of the liquid does have enough energy because it's not tied down, right? It has fewer neighboring water molecules, so fewer hydrogen bonds, so that it can absorb enough energy to overcome the IMF, the attractive forces between its neighbors, to get into the gas phase. Right? And this allows them to change phase, right, from liquid state to gas, right? Remember, the only difference there is the distance between the molecules, okay? So in evaporation, think of the surface of the liquid that is going to be very important in evaporation, right? So how big the surface of the water is will determine how fast the water is going to evaporate, right? And go into the gas phase. Okay, so here's the distribution of thermal energy. So only a small fraction of the molecules in a liquid will have enough energy to escape into the gas phase. But as the temperature increases, that fraction also increases because now you've increased the kinetic energy of the entire everybody in the container, right? And so that makes sense. The higher the temperature, the faster the rate of evaporation because you have increased the fraction of molecules that will have enough energy to break free of the IMF, right? Okay, let's think about condensation in terms of IMF. Condensation's the opposite, right? You're going from a gas back down to a liquid. Okay? So think of a gas just randomly moving around, right? These particles. Well, as they're moving around, they will lose energy, right? Through molecular collisions. It'll slow them down a little bit because what happens when things collide? Um, there's a small bit of attraction, right? And so then they lose a little bit of energy. So the result will be that some of the molecules will get captured back into the liquid phase as it is losing its energy, right? And it's making more collisions. So some may and stick together to form droplets, and we call this process condensation. Right? So it is about the IMFs, how well things condensate or things condense, because um, when the molecules collide with each other, there is an attractive force. That attractive force is the IMF, right? Um, so if the IMF is stronger, it's able to go back into the liquid phase more readily, right? Than if it's weak. Okay, so evaporation versus condensation, they're just opposite processes. Um, And if you have an open container, say, of water, right, eventually all of the water molecules will escape into the vapor phase because um, you have, uh, right? Every time that the top layer of the water molecule evaporates, it exposes a new layer, right? And so that ambient room temperature will eventually um, evaporate all the water. If you want to evaporate the water faster, what can you do? You can throw the water on the floor, right? And the water, since it's spread out, you have greater surface area. Remember, it's the water molecules on top of the surface that's going to escape into the gas phase first. So if you spread it onto the floor, you're going to make it, quicker to evaporate. Okay, now the interesting thing comes when you have a closed container, right? And so the gas molecules can't escape. So where can it go? Well, it can go up into this headspace. That's what we call it, right? It looks empty, but it's not. We know it's not empty. First of all, it has air in it, but it also has water molecules up there in the gas phase, right? Because with the stopper here, it can't just keep evaporating like in the open container. Okay, so the gas molecules will go into the gas phase, but then it gets stopped by the stopper. So now we got water vapor up here too, okay? So you got three scenarios here. In A, this is, earlier in time, you just stoppered the flask. So um, immediately what you're gonna get is just the evaporation of water into this headspace. So that's represented by the upward arrows here is the evaporation rate, okay? So first you only have evaporation, okay? But then as you put water molecules into this headspace, they can collide with each other and condense back down to become a liquid. So you start to see small downward arrows now. Those are the rate of condensation, okay? Some other time later, right, even more water gas molecules are up there. And so the rate of condensation grows as well. Until when? Until the rate of evaporation, the upward arrow, is equal to the rate of condensation. And this is where we have what's called dynamic equilibrium. Dynamic meaning this process is going forever and ever, right? You always have water molecules going into the gas phase. You always have gaseous water recondensing back down, but they're just doing it at the same rate, exactly the same rate. So you will always have the same amount of gas particles in the headspace and the same of liquid particles down here, right? So that's why it's called dynamic equilibrium. Here's another like a graphical way to think about reaching dynamic equilibrium, right? So again, at the very beginning, when you stopper the flask, you have the rate of evaporation, and it's quite constant because you have, a whole bunch of water in the liquid phase. And so it's just putting it into the gas phase, putting water molecules in gas phase at a very constant rate, right? So we call that the rate of evaporation, okay? It's the rate of condensation that changes because at the beginning, there's nothing to condense, right? There's no water vapor up there to condense. So it starts at 0, okay? But then as you evaporate more water, now there's water molecules in the gas phase bumping into each other and it's able to recondense. So the rate of condensation starts to creep up. And it does so until it meets the rate of evaporation. And right when those rates are equal, we call that dynamic equilibrium, okay? So what that means is it doesn't matter how long you leave the flask there. There, at one point, after it's reached dynamic equilibrium, there's only so much water vapor in that headspace, okay? And then now if you take a pressure meter, for example, and you measure the pressure here of the water vapor, it will be constant, right? And later you'll see that we call that the vapor pressure of water, right? Okay, so how does IMF then affect evaporation and condensation? Well, let's think about evaporation first, okay? In order for things to go from the liquid phase to the gas phase, it has to completely break the IMF, right? The IMF is pretty much obliterated. So if you have a strong IMF, it's going to be harder to evaporate. Everybody agrees, right? If you have a strong IMF, it's going to be harder to evaporate. And so therefore you have to put more energy into it in order to get it to evaporate, AKA you have a higher boiling point, okay? And we have a term for that too. If you can't be evaporated easily, meaning you have a high boiling point, you're called non-volatile. Okay. It's non-volatile. But if you have a weak IMF, doesn't take that much energy to obliterate the IMF, and all of a sudden you're in the gas phase. So you're called volatile because you're easily evaporated. And therefore, you can also conclude that, you know, you must have a low boiling point, right? If you're volatile. Okay, so we can actually measure this, right? Now, every molecule is going to be different because every molecule has its own IMF strength. That's why every molecule has its own boiling point, okay? But we can also measure how much it takes for, to get a certain amount of that compound to go from the liquid to the gas phase. And we call this the heat of vaporization, or delta H vape for short. It's the amount of heat energy required to vaporize exactly 1 mole of the liquid. Okay. So it's always going to be in units of kilojoules per mole. And since you always need heat to vaporize, the delta H vape is always a positive number because it's always endothermic, right? You always require energy in order to do it. And it is somewhat temperature dependent as well, right? Because obviously it's going to be easier to vaporize things that are already warm than vaporize things that are cold, right? If you have two liquids, one is cold, one is hot, of course, it'll be easier to vaporize the hot liquid. And so that's why you see in this table where it has the heat of vaporization for several liquids and their boiling points, it has two columns, right? How much it takes to vaporize at room temperature and how much it takes to vaporize at that liquid's boiling point. So obviously, the column of delta H vape at the boiling point is always lower than the delta H vape at room temperature, right? So we can see by far here, water is the highest. Water has the highest delta H vape, the largest enthalpy of vaporization. Guess why? Because of hydrogen bonding, right? So very strong IMF. It's going to take much more energy to vaporize. So uh, that's why it's at the top of the list, right? Okay. So again, notice, the units here, right? Kilojoules per mole, and also the difference in the two columns. Diethyl ether, if we draw that out, you'll see that it is polar, but it doesn't have a very big dipole. It's polar, but not like by a lot. And so that's why it is sitting down here in last compared to, say, acetone and rubbing alcohol. Rubbing alcohol, remember, is also hydrogen bonding because it has the OH group, right? And so that's why its number is very close to water. But since water has two OH bonds, right, it still has a higher delta H, right? Okay, so let's do this example problem together. Calculate the mass of water in grams that can be vaporized at its boiling point with 155 kilojoules of heat. Okay. So we can go to the board for this one. We got 155 kilojoules of heat. And we're asked how much water can be vaporized in grams. So we're going to go back to our table, and it says at the boiling point. So we're going to be the third column here. Looking at water. Water has a delta H rate of 40.7 kilojoules per mole. Okay, so it's nice and easy calculation here, right? Start with what you're given, 155 kilojoules. And what's going to go on top? Well, you want kilojoules to cancel, right? So mole's going to go on top. So for 1 mole of water, it's going to take 40.7 kilojoules of heat in order to vaporize it. So how many grams of water is that? Well, 1 mole is going to be on bottom, 18.02 grams of water on top, right? Um, so that's going to give us 68.6 grams. Okay, so 3 sig figs because of that 155. Okay. Okay. You guys can do this practice problem here. Okay. Pretty easy. So let's move on. All right, let's talk about vapor pressure now. Okay. So remember those three flasks, um, and the third flask that reached dynamic equilibrium, which means there's a fixed number now of, uh, water vapor in that headspace. If you take a pressure probe and you put it to that headspace, you'll get a number. That is called the vapor pressure of water, right? Um, so it's the pressure that's exerted by the vapor when it is under dynamic equilibrium. Okay. So how does, again, IMF affect this? Let's see. If you have a weaker IMF, okay, that means the bonds between the molecules are not held on as tightly, okay? So it doesn't take that much energy to bring it into the gas phase. So therefore, you're going to have a higher vapor pressure, right? Because you're going to have more vapor. So you have a higher vapor pressure, and a higher vapor pressure correlates to a lower boiling point, right? Because you don't need as much energy to evaporate things. So that will result in a lower boiling point. And we call these kind of liquids more volatile liquids, right? Then the opposite's true, right? What if you have a stronger IMF? If you have a stronger IMF, then you're going to have a lower vapor pressure because it's not going to be as easy to vaporize. So you have a lower vapor pressure, which means a higher boiling point, and therefore a less volatile liquid. Okay, so let's see what happens when you disturb the dynamic equilibrium of a liquid. Okay, so let's look at these three scenarios. In scenario A, you are at dynamic equilibrium. Okay, so meaning the rate of evaporation, this upward arrow, is equal to the rate of condensation, so that there are a fixed number of gas molecules in this headspace. Okay, now what happens if you increase the volume? If you increase the volume, what you do is you decrease the pressure, right? Remember pervert, PV equals nRT? If you increase the volume, you decrease the pressure in this headspace. So the system will have to correct in order to bring everything back into equilibrium. So then it puts more gas into that headspace. So the rate of evaporation will increase if the volume is increased. Okay. What if the volume is decreased? Well, if you squish it now, that means you're going to increase the gas pressure in this headspace. And so to alleviate that increase in pressure, the gas molecules will condense. So the rate of condensation will increase. Okay. Pretty interesting, right? So this principle is called Le Chatelier's principle. Notice that that's actually how nature behaves. You put stress on anything, any system in nature, it will fight back. It will try to get back to, equilibrium or homeostasis, right? It's that idea, okay? That any system is going to resist change, okay? But in the sciences, in chemistry, in particular, we attribute that to Le Chatelier. So Le Chatelier studied a lot about equilibrium, and that's Le Chatelier's principle is when conditions change, the system will shift its position to relieve or reduce the effects of that change. Okay. And so we saw that here, right? If you increase the volume, then you're going to make the rate of evaporation faster. And then if you decrease the volume, then you make the rate of condensation faster. Right? Okay, let's talk about the temperature dependence of vapor pressure. So what happens when we increase the temperature? If we increase the temperature, we're going to get more kinetic energy of the liquid molecules, and therefore vapor pressure will increase, right? Because it's going to be easier to put them in the vapor phase. So actually, even small changes in temperature can make a huge difference in an increase in vapor pressure. And the rate of this growth, of course, is going to be tied to the strength of the IMFs, right? If the IMF is really strong, then the changes are going to be smaller, right? If the IMF is weak, then the changes is going to be bigger, right? So let's take a look at the graph that compares four different liquids here: diethyl ether in yellow, ethyl alcohol in cyan, water in magenta, and ethylene glycol in is light blue. Notice that what we see is as we increase the temperature, the vapor pressure increases. Okay. So no surprise there, right? We already know that. We can explain that. But what's interesting is this horizontal line here, okay, at 760 vapor pressure. So 760 torr. Remember what that unit is. Torr, one torr is the same thing as 1 millimeter mercury, and 760 millimeter mercury is 1 atmosphere, right? So this line is telling us, okay, at sea level, what is the boiling point of each of these liquid? Is where the vapor pressure meets that horizontal line. Okay? So then we now have a scientific definition of what a normal boiling point is. A normal boiling point is when the vapor pressure of any liquid meets the atmospheric pressure at sea level, right? So that's why it's called normal. So of course, the boiling points of things can fluctuate, right, based on your altitude, right? So you can see that for water, where it meets that horizontal line is at 100 degrees Celsius. And so that's why we say water boils at 100 degrees Celsius. Well, certainly here, yes, because we're at sea level and we do see that, but it's going to change, right? If you change your altitude. So ethyl alcohol boils at around 78.3, diethyl 34.6, ethylene glycol at some much greater temperature. Okay, so the boiling point, what is it that exactly? We are defining it, right, again, as when the vapor pressure is equal to the external pressure, okay, um, is when you'll get boiling, okay. So you can see how boiling is reached, right? So if you are looking at, say, uh, a flask on a stove, right? You can see that the bubbles are forming at the bottom, okay? And that bubble is forming because you have increase in the kinetic energy. So the water molecule is kind of like making room, right? It's like going like this, and it's actually making little pockets. Those are what bubbles are. Now, if the atmospheric pressure is greater than the vapor pressure inside, it will smash the bubble. And so you don't get boiling, okay? But as you add more heat, what happens? You increase the vapor pressure inside the bubble until it is equal to the atmospheric pressure. So it gets propped up. It does not get popped anymore, right? It can prop itself up. And then, of course, if it can sustain that, the bubbles will rise because it's less dense than the water. And so that's why you start to see the rolling boil, okay? So that's the technical definition of boiling, is that when the vapor pressure is equal to the atmospheric pressure. Now, the atmospheric pressure can change, right? So the boiling point of liquids can also change based on altitude. Okay. So we know that when we go up in altitude, right, the air gets thinner, meaning the atmospheric pressure decreases. So what does that mean for boiling point of all liquids? At higher altitudes, they will also have to decrease. All right. So for example, where we are sea level, right? So our water boils at 100 degrees Celsius, right? But if you go to the Mile High City, where we call that Denver, Colorado, you're going to see that water actually boils at 94, which would be really weird if I was to teach chemistry in Denver, right? And I'm like, oh, water boils at 100, and nobody believes me, right? But yeah, it's truly, it's kind of a problem for them there that their water doesn't boil at 100, right? Um, Now, if you go, let's say you go to Mount Everest, which is the highest peak on Earth, you'll see that water boils at 78. 78. It's warm, right? It's not, how's that considered boiling, right? It's actually just warm water. But you'll see that water is actually going to a rolling boil there. Okay? And that's because the atmosphere there is only 0.32. Okay. And we're defining normal boiling point as vapor pressure becomes as great as external pressure. So external pressure drops, so does boiling point drop. This is a big problem because why do we cook our foods? You want to kill the bacteria, right? But now you're boiling water. Your water is boiling at 78, but it won't get any hotter. So how's it going to kill bacteria? Right. So it poses a challenge for people that are living up at higher altitudes. They'll have to use like pressure cookers, or the people that climb Mount Everest. I mean, they're not even cooking, right? They're just eating like dehydrated food. But let's say you do want to cook food at altitude, you will need to either cook your food for a lot longer, but if it doesn't even come to a boil, you can't kill anything anyway. So you better use a pressure cooker, right, in order to do that. Okay, we'll get to the last part of this chapter. We're gonna do some calculations here. So we've been talking everything so far, just uh, in terms of quality, right? Just qualitative analysis. Now we're actually gonna calculate how much energy is gonna be put in heating things or boiling it, um, or melting it. Okay. So first you have to learn about the heating curves. So heating curve of a liquid is shown here on the right. So you can see that temperature is on the y-axis, heat added is on the x. So let's say that you have a liquid at initially 20 degrees Celsius. So that's this data point right here. Okay. As you add heat, what happens? It'll ramp, right? So temperature will increase, temperature will increase, temperature will increase until, um, and this liquid, by the way, is water. Okay. So water at 20 degrees Celsius gets heated up, and then all of a sudden you add heat, but the temperature doesn't change. It just flatlines. Okay, that's weird. Well, I'm adding heat. Why is my water not heating up? Oh, wait a minute. Well, at 100 degrees Celsius, I'm no longer water, right? Water turns into steam there. Okay, so the way you can think of this flat line is a phase change. And how do you explain that it's flat? Well, all of the energy is going into breaking the IMFs, right? So not until all of your liquid turns into steam do you ramp again in temperature, right? Because all of the heat that is being added is going into breaking the IMFs until every single last water molecule is turned into steam, right? And then here, everybody's steam, and then you keep adding heat, and then it's just like hotter and hotter steam, right? Until you top out here at 140 degrees Celsius steam. Okay. Okay, so to calculate this, what you need is at every ramp, you have a change in temperature, right? And we already know an equation for that. Q is equal to MC delta T. So whenever you have a ramp, meaning you have a delta T, you can use this equation. Q measures the heat, remember? Is equal to the mass, so how many grams? Grab the specific heat of that liquid. It'll be water here, right? Then times the change in temperature. So for example, if you're looking at the first ramp here, the change in temperature will be, where was it from? From 20 degrees to 100. So final minus initial for delta T, right, is 100 minus 20, which is an 80-degree change in temperature, right? That's how you do it. We're gonna skip this here. This here is called the Clausius-Clapeyron equation. You guys can study it on your own, but just in the interest of time, yeah, I'm not gonna cover it. And so that also means if you encounter problems like this in the homework, you can skip it as well. And I'm not gonna put any of it on the exam. Okay. All right. So let's talk about what a supercritical fluid is. So let's say that you have a liquid that is completely in a sealed container, right? Very sealed container, very airtight. It's not going anywhere. And you just start heating this chamber. Okay? So this is the beginning. This is what would it look like, right? You have liquid, which is more dense, so it's going to be at the bottom. Then the gas is going to be at the top, and you can see the interface, right? So then as you heat this fluid, what happens is it's going to put gas molecules into this space, okay? Which means it's going to make the top space more dense, right? While the bottom phase gets less dense, okay? And since the fluid has nowhere to go, all you're doing is you're doing this change in density. So eventually what happens is the the gas phase, the top part of the chamber gets more dense, and the bottom part of the chamber gets less dense until they are exactly the same density. So you no longer see this line, right? This division between a liquid and a gas. You just see this. It's all the same. This is what we call a supercritical fluid. It has reached a point that it is no longer distinguishable as a liquid or a gas, right? So really interesting uh, result, right? What a supercritical fluid is. Okay, let's talk about a critical point. The critical point is the temperature required to produce a supercritical fluid, right? So to produce this, you need a critical temperature and you need a critical pressure. It can't just form at any given moment, right? Uh, Not until you reach the critical point, which is some critical temperature and some critical pressure, are you able to make a supercritical fluid. So the critical temperature or higher temperatures, or at the critical temperatures and higher, the gas cannot be condensed to a liquid, no matter how high the pressure gets. Okay, let's talk about another phase change, sublimation and deposition. So sublimation is a process where a solid goes straight to the gas phase, skipping the liquid phase. That's called sublimation. And deposition is the opposite. It's when gas molecules go straight to the solid phase, skipping the liquid phase. So they are, opposite of each other. Okay, let's talk about melting, or AKA fusion. Same thing. Melting is going from a solid to a liquid, right? And when you're going from a solid to liquid, you are increasing the kinetic energy by adding heat, and that heat is loosening the IMF, right? It's not breaking it completely because it doesn't need to go into the gas phase, right? But it does loosen it so that the molecules can roll past each other, and that's what we associate with the liquid phase, right?